All right, so with that question, I think I need to probably need to go over the schedule. So today I'm gonna go over uh, quite a few examples of how to do statistical testing in using StatKey. Um, and then that'll be today. And then next Monday will be a quiz, which will be on hypothesis tests. So it'll be similar to the last quiz, where I'll be putting some StatKey um, graphs into Canvas. Um, just remember that I'm going to post some sort of over the weekend, late weekend. I'll post some sort of test quiz or something where you can go in and whatever device you're using, you can test to see if you can open up one of these um, StatKey graphs. Just make sure you can do that before you take the quiz. All right. So reboot your computer, whatever you need to do to make sure that it opens up. It should open up because it's just a picture. It's a picture file, PNG file. So it should be able to, you should be able to open it up on your computer. So again, pop-up, you might have pop-up problem. Should make sure that pop-ups are allowable on Canvas. So, you know, pictures can appear and things like that. And so we'll have a quiz next Monday. We'll have a review for our test. Our final test will be next Wednesday. And it'll cover everything on probability, all the things, chapters that dealt with probability, confidence intervals, and hypothesis tests. All right, but I'll go over the what you need to review on Monday. All right, and then the following Wednesday, a week from next Wednesday, it's 2 weeks from today, will be your final exam, and it's from 2:45 to 4:45. So you should have already received an email a couple weeks ago regarding that. Okay, so that's it. So what I'm going to do, I created a little bit of a handout, which I'll post. Yeah, actually pick that up. All right. I'm calling this hypothesis testing instructions. It is a simplified version of what you would do as if you were taking a regular statistics course, but it still involves several steps. So the first step would be to state your null and alternative hypotheses symbolically, not in in a sentence, symbolically. So examples would be, and again, the problem, whatever problem I give you, it'll be clear what the hypothesized value is. So the null hypothesis will always have an equal to sign, and it was always stated as an H sub 0 with a colon next to it, and then the population mean or proportion is given, and in this case, as an example, we have our null hypothesis as mu is equal to 100, and I would say something like versus the alternative hypothesis, which is H sub A, mu is less than 100. So when it's less than, we have what's called a left tail test. All right. We have a right tail test, which means the null hypothesis, again, will have an equal to. In this case, we're giving an example with a proportion. So again, this is just an example. P is equal to 0.27 as a hypothesized value. And then the alternative would be P is greater than 0.27. Again, these numbers have to match. The null and alternative numbers have to match. And that's called a right tail test because there's a greater than symbol in the alternative hypothesis. And then the third type of test would be again, I'm going to use mu as an example. Mu is equal to 50 is our null hypothesis versus mu is not equal to 50 as the alternative hypothesis. All right, that's called a two-tailed test. So the problem, whatever the problem is in words, will basically give you a significant clue of one of these three cases. All right. There'll be something that says that the researcher is interested, for example, in values of the they think that the population mean is less than 100, all right? Or they'll say the population proportion is greater than 0.27. They'll say something like that. Or they'll say, I think it's different from 50. Then you would use mu is not equal to 50. So the words of the problem should give you the clue about which of these three cases we would use for the alternative hypothesis. The alternative hypothesis defines the type of test, whether they're a left-tail test, right-tail test, two-tail test. As you'll see, I'll give you examples today in StatKey for all three of these. So you know how to actually create one of these in StatKey. Now, you won't have to actually create one in StatKey for the test because the problem is these are simulations. StatKey creates simulations so that the actual values that show up on your screen, the distributions for both the confidence intervals and hypothesis tests, they're going to be different from person to person. So basically, I'm going to give you one and then ask you questions about it. But if if you're ever taking a quiz or a test, you'll have access to StatKey. You can open it up, and if you're not sure what to do, you just go into StatKey and play a little bit with it just to refresh your memory. Okay, now, once we created our null and alternative hypothesis, we need to create a randomization sampling distribution. That's one of those graphs that I've been showing you, and you create it in StatKey. So you're going to create it, or it's going to be created for you. Number three is, and this is an important thing, is there's going to be a sample statistic for the problem that you're going to be given, either a sample mean or sample proportion. And your job is to plug that into one of the endpoints in the distribution, and I'll show you how to do that. And once you plug it in, there's going to be a proportion shown, basically those red dots, that area of the distribution. There's going to be an area that you're going to look at, and it's going to be a number with reference to that proportional area, and that's going to be what's called the p-value. All right, and basically for the left tail test, where the alternative hypothesis says less than, you would plug in your sample statistic into the distribution, and then you would find the p-value. The p-value would be the area to the left, or the probability to the left of that sample statistic. For right tail tests, where the alternative hypothesis has a greater than symbol, you're going to be looking at the right tail instead of the left tail, and you're going to plot your sample statistic, and the area to the right of that sample statistic, or the proportion to the right of it, is your p-value. For a two-tail test, you're going to plug in your sample statistic again, but this time you have two tails, and you're going to actually add up the proportions or probabilities in the two tails. You're going to add them up, left tail plus the right tail proportions, and that sum will be your p-value. Once you have your p-value, you're going to compare it to alpha. That's the probability of a type 1 error, or level of significance. Here's the rule. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. It's as simple as that. Once we have our p-value, compare it to alpha, determine whether it's one of these two cases, and then you get your decision. Typically, once you have your decision, you write some interpretation, but again, if I give you a multiple choice test, the interpretation will be given, or possible interpretation, but the correct interpretation must include a brief phrase at the beginning of the interpretation that says something like, at the 5% level of significance, or significance level, or at the 1% significance level, something like that, which is referencing our alpha. You convert the alpha as a decimal to a percentage, and then you just state something like this. And the reason will be apparent in a minute, right? So you say something if you're going to reject a null, you say something like, at the 5% level, significance level, there is enough evidence to reject the null hypothesis, something like that. All right, so that is the 6 basic steps that's involved in the hypothesis testing. It is a much simpler set of steps than if you were taking a statistics course where there would be formulas And there would be variation in the formulas due to certain circumstances. Much more complicated steps are in hypothesis tests. This is really a fairly simple, straightforward procedure. As long as you know what you're doing, it's pretty easy to do. All right, so let's stop sharing this. And I'm going to go now into StatKey. Let's make sure StatKey is open. Second. Yep, it's open. Okay. So let me share StatKey with you. Once again, this is the main screen for StatKey, and the third column here, where it says randomization hypothesis test. This is the place where you would run hypothesis tests. As a student, you can always go in here and you can play around. You're not going to break anything. Definitely not. And the hypothesis tests are the first 4 that are listed here. The first 4 I'm going to go over today. This last one here is not going to be done in this course. It's an advanced one, which is not something we would do. Also down here, they say more advanced randomization tests. Absolutely not in this course. Okay. So, if you want, obviously, if you want to play around and you want to do your own reading and you're interested in it, you can certainly go ahead and do whatever you like in those. But what you're responsible for this course is this column here, the first 4 tests. So the first one we're going to do is the test for a single mean. And this is what the screen looks like. Again, you're going to have, data, possible data files in here. And you'll have an original sample, which are the data files. All right. So I think we had gone over this one last time. Let me find another one that we can do. All right. Information difference. This might be a little confusing. Let me actually give you another one here. Let's do mammal gestation days. Okay. All right. So these are 40 mammals. I don't know where they got them from random sample of 40 mammals with the number of days of gestation. Different mammals have different gestation periods, right? So ours is obviously out here, in this area here, and here's a mammal that has a gestation period 645 days. Right? So and then there's some that have much lower gestation periods, 21-day gestation period. Anyway, there's 40 of these mammals, and the average gestation period for the 40 mammals is 194.325 days. That's your average. And we're going to create what are called randomization samples. That means we're going to, using the hypothesis, the null hypothesized mean, we're going to randomly create samples of size 40. For example, I can create one right now. 40 random mammals. And this sample mean is 217.575. So the sample means are going to be close to the actual hypothesized mean that's given. In this case, it's 200. But if you wanted to change it, you just click in here. And actually, I could change it. No problem. Let's make it 190 instead of 200. All right. Therefore, the randomization samples that are chosen are going to be closer to 190. I can choose several of them, close to 190. Let's just create 1,000 of these, maybe 2,000. Let's create 2,000 samples, size 40. These are randomization samples. Now, remember the null hypothesis is 190. Mu is equal to 190 is the null hypothesis. I've made that the null hypothesis. And let's say the alternative hypothesis, after we've read this, let's assume that the null hypothesis is, the alternative hypothesis is that the true mean is actually greater than 190, right? So the researcher's saying, I don't think it's 190, I think it's probably 200 or 210 or something. But I'm going to just state it's greater than 190. Since the alternative hypothesis says that mu is greater than 190, we're going to use a right tail test. Click that box there. And automatically it defaults to 0.025 for this area to the right here. This, in other words, 2.5% of all these 2,000 dots, all right, are going to be, and I believe that's 50. There's 50 dots here on the right. That would be the the percentage of the dots that are in this area, this range here in the right tail. If we wanted to plot the actual sample mean, 194.325. Remember, this is the original sample mean. Ignore what's down here. This is just the last one of these samples that we crossed over. The 194.325, if we actually click this box down here and we plot that 194.325, it's plotted right over here, okay, pretty close to 190. Notice that the area to the right is now 0.425. That proportion of the 2,000 samples is 0.425. Now, a definition of a p-value, it's the probability of getting that sample statistic, in this case 194.325, or something more extreme than that. That means further away from the hypothesized value of 190, if we assume that the hypothesized value of 190 is true. All right. If it's true, then the probability of getting a 194.325, the sample mean that we got, or something more extreme than that, is 0.425 or 42.5% chance. That's pretty high. But that's what's called the p-value. All right. It's the probability of getting the sample or something more extreme than the sample when we assume that the hypothesis that the mean for the population is 190. So in this case here, it looks as if, I mean, if we weren't going to do anything more than this, it looks as if that the sample of 194.325 is something that we could assume to be fairly normal as a variation around that population mean. All right, get something like 194.325. It's not unusual because there's a 42.5% chance that you're going to get that or something more extreme than that. Now, how do we actually do the hypothesis test? Well, once what I stated before was, once you calculate this p-value, you're going to compare it to the alpha. Alpha is what? It's the probability of getting a type 1 error. It's the probability of rejecting the null hypothesis when the null hypothesis is actually true. In this case, the null hypothesis is 190. So what you're basically saying is, when you remember, a researcher selects this alpha or level of significance before they do the research. So what they're really saying is, when they select that alpha, is that they are willing, the researcher is willing to accept up to a 5% type 1 error. That is, when they reject the null hypothesis, that the null hypothesis is actually true. We're willing to accept a 5% chance of that happening, or something smaller than that. But they're not willing to accept anything bigger than 5%. So if the p-value that we actually get is less than or equal to alpha, that's acceptable to us, so that we can reject the null hypothesis. We'll feel comfortable rejecting because it's a probability of less than the type 1 error. So that's fine. We'll accept that. But we won't accept a probability greater than 0.05. In this case, 0.425 is much larger than our alpha of 0.05. So we do not feel comfortable in rejecting the null hypothesis. It's likely that the null hypothesis is true. Even though we're not sure, it's possible it's still false. But because the type 1 error, the actual type 1 error, the p-value is actually the way you could look at it. It's the actual type 1 error. Since the actual type 1 error is 0.425, that's too high. You know, ahead of time we said 5% is the highest we'll go with type 1 error. Well, this is much higher than that. So therefore, we're not going to take a chance. We're not going to reject the null hypothesis. So we say in essence, there's not enough evidence to reject the null hypothesis at the 5% level of significance. All right, so that's the rule. Once again, the p-value is less than or equal to the level of significance that we choose, then we feel comfortable in rejecting the null hypothesis. If the p-value is greater than the level of significance that we choose, then we do not feel comfortable in rejecting the null hypothesis. That's our decision not to. And that's the rule. That's the way we do this.
Can you repeat?
Yes, go ahead.
Can you repeat it, please?
Repeat what?
If the p-value is negative, then
No, I didn't say it was negative. If the p-value is less than or equal to alpha, alpha, remember, is the level of significance, then we reject the null hypothesis and we support the alternative hypothesis. If the p-value is greater than alpha, then we do not reject the null hypothesis. That's the rule. It's in the, I'll post that sheet that I showed you at the beginning, the one that I showed you the 6 steps. This is one of the steps. All right, but yes, write it down. That's a good idea. All right, so that's one example of a hypothesis test. All right.
Wait, I have a question real quick, just one more time.
Yeah.
If you said if the p-value is greater than the null hypothesis, I think you said, then, or no, if the p-value is greater, do you reject or?
All right, let me say it again. Yeah, let me say it again. Actually, let me stop sharing this for a second. I think it might be better just for you to see it instead of hearing it. So let me share that these steps again. You don't have it. I haven't posted this yet, so I understand that you're not sure. So here, let's look at step number 5 here. So here it is right here. Remember, alpha is the level of significance. Alpha is the level of significance. It's stated in the problem. It's the probability of a type 1 error. So if the p-value that you get based on the sample statistic is less than or equal to this alpha, which is stated as it's going to be a small number between 0 and 1. It's going to be typically 0.05, 0.01, 0.1, something like that. P-value is less than or equal to alpha, we reject the null hypothesis. Okay. P-value is greater than alpha, we do not reject the null hypothesis. All right, so everybody who's questioned that or everybody else too, write that down right now into your notes. Because again, you don't have access to this right this moment. All right, give you a minute to just write this down. Okay. Anybody need more time? Yell out if you need more time. Are you okay? All right. So let's get back to stacking. All right, so let's now look at an example of the difference between two means. Sometimes, now this is just one population, right? One population of mammals. Suppose we're comparing two populations and we're measuring the same thing. These two populations are independent of one another. So StatKey has that test for difference in means. So many times we want to know if there's any difference in the means between two groups. Okay. All right. Let me find someone that one of these things. Commute time. Here we go. Commute time. Atlanta versus St. Louis. All right. These are commute times in, I believe, probably in your car. That's my guess. Driving to work, from home to work, or work to home. And these are, for each one of these cities, there are 500 commuters that were sampled. And each of these bars here represents different numbers of commuting times in minutes. Like this is 20 minutes, all these are 20, all these are 15 minutes, 30 minutes, and all the way up to, there's somebody has 130-minute commute. Okay, 130 minutes over 2 hours, that's crazy. All right, and anyway, same thing with Atlanta, 500 commuters in Atlanta. Now, Atlanta basically is group one. Typically, when we have two populations with means, the group one is on the bottom, and group two is on the top. All right. So group one, the Atlanta commuters, have an average commute time of 29.11 minutes. That's the X1 bar. X1 bar, this one here. And then the St. Louis commuters have an average of 21.97 minutes for their commute time. That's X2 bar. So if we subtract those two means, 29.11 minus 21.97 is 7.14 minutes. So basically, Atlanta commuters on average commute 7.14 minutes more than St. Louis commuters. That's basically what we're saying. All right. Hopefully that makes some sense. Suppose we want to, suppose our null hypothesis is that the two population commute averages for both St. Louis and Atlanta are the same. We're assuming in the null hypothesis there's no difference between Atlanta and St. Louis in average commute times. Okay. And notice that there's no choice here with the stat key. That is our null hypothesis, that the two commute time averages for the two populations are equal to each other. Now, I hope you could see algebraically that if we subtracted u2, the variable u2 from both sides of these equations, we would have u1 minus u2 on the left, and we would have 0 on the right. So when we say u1 is equal to u2, it also means that u1 minus u2 is equal to 0. All right? So the null hypothesis in terms of the difference in means would be 0. u1 minus u2 is 0, because we're assuming the two commute time averages are equal. And we want to know, let's say in this particular case here, I'm just going to make this up. Suppose I want to know whether the average commute time, the difference in the commute times is larger for Atlanta than for St. Louis. Okay. Maybe Atlanta is a bigger city. It has much worse traffic. And you think that on average, Atlanta commuters will have longer commute times than St. Louis commuters. Now, Atlanta, again, is population 1. St. Louis is population 2. So what you're assuming is that u1 minus u2 is greater than 0. All right. Atlanta is greater than St. Louis. All right. So since we have a greater than symbol in our alternative hypothesis, that is, u1 is greater than u2, or u1 minus u2 is greater than 0, we're going to use a right tail test. So we're going to click that box. So we're going to generate a couple, maybe 3,000 of these randomization samples. And we're going to click the right tail. Yeah. Now, once again, what we're going to do is we're going to take our sample statistic, in this case 7.14, and we're going to replace it into this box down here. We're going to, in other words, plot it along this x-axis and see where it is. Now, obviously, it's going to be way to the right here, but I'm going to do it anyway. Let's plot it, 7.14. Notice it plots it way down here. So far away from not only 0, but from all the different plots for the 3,000 samples that we created, with different differences in the commute times. So 7.14 is highly unusual. It's so unusual that there were no randomization samples that were at least this amount or greater. So we see actually 0 in this case as our p-value, 0. Now, in real life, p-values are never exactly 0. They may be something really small, like, 0.00001 or something like that. But for all intents and purposes, when we have a p-value extremely small, like the number I just gave you, we could say the p-value is approximately 0, which it is in this case here. Well, if you get a p-value that's small, you know that you're going to reject the null hypothesis. Because remember, null hypothesis is when the p-value is less than or equal to, excuse me, the rule, the decision rule is that when the p-value is less than or equal to alpha, you're going to reject the null. Well, I don't care what you pick for alpha. You're never going to pick a number lower than 0.01. Well, this 0 is going to be less than any alpha that you pick. So this is where you say it's highly significant result. This is so highly significant that there's practically a 0% chance that the true difference between Atlanta and St. Louis is 0. In other words, it's highly significant and highly probable that Atlanta's commute time is significantly higher than St. Louis's commute time. Right? Because the chance of getting 7.14 as a sample difference, when you're assuming no difference, is practically 0. There's hardly any chance of that happening. So in this case, the answer is reject the null hypothesis. Any questions about that? That's pretty clear, right? If you get a p-value 0 or close to 0, it doesn't matter what you pick for alpha, right? You're going to get 0. You're going to get 0 being less than whatever number you pick for alpha. All right. Let us now. So that's the difference in means. So we've done one for a mean, and then we've done one for the difference in means. Let's do one for a proportion. Hypothesis test for proportion. It's a single proportion. We'll do this one here. Now, we do have a choice here of what we want our hypothesized proportion to be. Remember, a proportion is just a count of the number of people answering a question a certain way divided by the number of people that we ask the question to, right? That's so if we survey 100 people and 25 people answer yes to a question, that means 20.25 is your proportion of people who answer yes. It's 25 divided by 100. Suppose let's make this 0.75. Right? I'm just making something up here. So suppose our hypothesized proportion is 0.75. And suppose our sample, I'm going to change the sample here. I'm going to say out of 100 people, 70% or 70 of them said yes to a certain question. So this is our sample proportion, 0.7. So the hypothesized portion is 0.75. We get 0.7 as our in our sample. And suppose our alternative hypothesis is that the hypothesized proportion is incorrect. In other words, we're not sure whether it's incorrect low or incorrect high, but we think it's incorrect, which means that our alternative hypothesis is that p is not equal to 0.75. We're not sure which way it's different, but we're quite sure it's different than 0.75. So when we have an alternative hypothesis that says not equal to, that is a two-tailed test. Did we do a two-tailed test yet? I don't think we've done one yet. So we've done a left-tailed test and a right-tailed test. So we're going to do a two-tailed test here. All right, we're going to click that box when you're ready. Suppose we're going to create maybe 2,500. Maybe no. Let's do something smaller than that. Portions. Let's make 500 samples. Each one will have a size of 100 in each sample. And we just run our, cursor over any of these, and we'll see different counts. 77 for this one, divided by 100 is 0.77 for a proportion. Down here, 70, well, let's do another one. Here's one that is 69 out of 100, 0.69. So these are the randomization samples, right? These are just randomized samples. Each one of them are size 100. Each one of them will have different count with a different proportion. Now, we're going to do a two-tail test here. We click the two-tail box. And automatically gives us red on the left, red dots on the right. And what we're going to do is we're going to plot the sample proportion down here. Now we have two boxes to choose from. Which one do we pick? Well, we take a look at what the null is. The null is 0.75, and we look at our original sample proportion, 0.7. Well, that's to the left. So we're going to click the box to the left. That's how we figure it out. We look at our sample proportion. Is it less than the null? Is it greater than the null? If it's less than the null, you're going to use this box. If it's greater than the null, you're going to use this box. So 0.7, our sample proportion is to the left. We're going to click that, and we're going to type in 0.7 as our sample proportion. Okay, so what has happened here? We have 0.7 on the left. It automatically gives you the another endpoint on the right, but we put 0.7 here. And we see that the number of red dots to the left here amounts to 0.16 of the 500 dots, or 16% of all the dots. But there are a corresponding same number of dots on the right. Okay, red dots to the right. Again, 0.16 is the proportion of those. So the question is, what is the p-value? Well, for a two-tail test, we're going to add this box plus this box. So that's what you have to remember. When you do a two-tail test, you add the two-tail probabilities. The two p, so each one of these, by the way, is half of the p-value. So when we add them up, you get the total p-value. When you add these two numbers, you get 0.16 plus 0.16, it's 0.32. Notice if you took the middle number here and subtracted it from 1, you get 0.32. So your p-value is 0.32. It's not 0.16. It's the sum of these two, or one of them times 2. But it's 0.32. So your p-value is 0.32. Now, what if my alpha is 0.10? 10% level of significance, 10% probability of a type 1 error. Based on the decision rule, comparing the p-value and alpha, can you tell me in this case here whether you reject or do not reject the null hypothesis? I hope somebody is paying attention. I'm not just talking to myself. Is anybody? There's only two possible answers. So, but give me a reason why when you
Reject.
tell me. Go ahead. I heard somebody saying something. Go ahead. You don't even have to share who you are. Just tell me what you think. Are you going to reject or not reject the null hypothesis?
Can I say what I think?
Yes, go ahead.
Do you reject the null hypothesis?
Oh, all right, and tell me why.
Because the p-value is 0.32, and the level and the I think level of significance is 0.68.
No, the level I mentioned, the level of significance is
it's the same
0.10. 10%.
The number in the middle is greater.
No, let me say it again. First of all, in this stat key, the whole page here, when you look at it, there's nothing on here which asks for alpha. Alpha does not appear at all on this. You can't enter it anywhere. Well, you can. There's an alternative way of doing hypothesis tests where you will enter alpha, but if you're doing this p-value method, alpha's, you don't see it. In other words, it's going to be given to you in the problem, on a separate piece of paper, you'll see it written down. All right. What I'm telling you is, in this case, alpha is 10%. That's the probability of a type 1 error. That's the level of significance. So if alpha is 10%, and you're correct, the p-value is 0.32, look at the decision rule that you wrote down. And do you reject or do not reject the null hypothesis?
Do not reject.
Do not reject, and tell me why.
The p-value is 0.32, and you said the other one is 10%, which is 0.1, so p-value is greater.
Right. The other thing meaning the alpha, the level of significance. So when the p-value is greater than the level of significance, which it is in this case, 0.32 is greater than 0.10, we do not reject the null hypothesis. We do reject it if the p-value is less than or equal to alpha. So be careful. I understand what you were doing. You were looking at the 0.68, the person who talked before. That's not the alpha. Alpha is not 0.68. The alpha is not even seen here. It is the given in the problem. All right, so you'll see it. It'll be written as alpha. It'll be written as probability of a type 1 error, or it'll be written as the level of significance. Whatever way it's written, one of those three ways, that is the alpha that you're comparing the p-value to. And the number in the middle here is the number in the middle here is just is 1 minus the sum of these two numbers. That's what the number in the middle is. All right. So any questions about that? And now we're going to do a randomization test for a difference in proportions. So we have two populations now that we're comparing. And I think the one that we're looking at now is good enough. This is a good example. All right. So suppose we have 1,029 married couples, and we're going to assume we're going to assume that this problem came 30 years ago, and this is the way people thought 30 years ago. So all marriages were males and females. Let's just leave it at that. All right. So it's a outdated example, but let's assume this is the example. All right. So we have 1,029 married couples, males and females. Suppose we ask each person in the couple the following, and we ask them separately from each other. All right, so they're independent answers. We ask them, do you find divorce to be morally acceptable? All right, yes or no. And so we asked, so basically there was 1,025 males, 1,029 males, 1,029 females. They were asked independently this question. Out of the 1,029 males, 730 of them said yes, they found it morally acceptable to get a divorce. Out of the 1,029 females, 689 of them said yes. All right. Now, the way when we have two populations and when we're dealing with proportions, the first group that's mentioned here is group 1. The second one that's mentioned here is group 2. All right, so this is arranged a little differently than when we looked at difference in means, where we had like a graph. All right. So again, the way to become familiar with this is just to go in the stat key and play around a little bit. Go into these different ones and just pick one of these examples and just take a look at it and see how it works. All right, now, if you took 730 of the males out of 1,029 total males, the 730 said yes, morally acceptable divorce. You divide these two numbers, you get 0.709 as the proportion of males who find divorce morally acceptable. For females in the sample, 689 out of the 1,029 of them. If you divide those two numbers, it's 0.67. So the difference in group 1, which is the males, and group 2 is the females, the difference in their proportions is approximately 0.04. 0.04. All right. So that is the sample difference in proportions. In other words, it's P1, my P hat, the little hat above the P here represents a sample proportion, minus P2, which is group 2's sample proportion. That's what they're referring to here. So when we plot what's called a randomization sample, all right, we're randomizing around what? Now this is important. I have to tell you before I pick the randomization sample, how does it do this? Well, the null hypothesis for all differences in proportions in StatKey is that the two proportions are equal to each other. In other words, there's no difference between males and females in answering this question. If we subtracted P2 from both sides of this equation here, we would get P1 minus P2 is equal to 0, which indicates the difference between the two groups is 0. So the alternative hypothesis, hold on one second here. Hold on a minute. That's pretty funny. My smartphone was in here and somehow Siri got on and she said, uh-huh. She was actually listening to what I was saying and then asked a question on the phone. That's really weird. So I moved her out of the room. So anyway, suppose we do a two-tailed test also on this one. Let's do a two-tailed test on this one. Let's say we believe that no, actually, let's do a right-tailed test. Let's do a right-tailed test. Let's assume that males, we think that more males find it divorce acceptable than females. So since the males are group 1 and the females are group 2, we're basically saying as an alternative hypothesis that P1 minus P2 is greater than 0. All right, does that make sense? So we're saying we're thinking males are gonna think divorce is more acceptable than females. So this would be a right-tailed test because we're saying P1 minus P2 is greater than 0 as our alternative hypothesis. So we're going to end up clicking the right box here. We're going to set up some couple thousand of these examples of these samples, and we're going to do a right-tailed test. Once again, it defaults to 0.025. Now, what are we going to put into the box here? We're going to put in our sample difference between males and females, which is 0.04. Now, by the way, I have to tell you that when you're doing difference in proportions, and the null difference is going to be 0 in this case, the negative is indicating what? These negatives are going to be indicating that females find it more acceptable than males. The dots that are positive indicate that males find it more acceptable than females. But in our sample, males are finding it more acceptable than females by a difference of 0.04 in terms of the proportion. So I'm going to type in 0.04 down here as our sample proportion. Sample difference in proportions. And notice what shows up here is our p-value. This is the probability of getting a sample proportion of 0.04 or greater than that if we assume no difference in the proportions between the two groups. We're assuming that males exceed females by 0.04 or greater. The probability of that is 0.026. That's our p-value. Suppose my alpha, my level of significance is 1%. My question to you is, what is your decision? Do you reject or do not reject the null hypothesis? Once again, the alpha, the level of significance is 1%.
You reject it, right?
Okay, and tell me why.
Because the p-value would be less than the alpha.
All right, does everybody agree with that? Let's get a second confirmation, or maybe somebody else has another opinion. Anybody else want to comment?
I agree with her.
You agree with her? All right. Now, a 1% level of significance, when you convert it to a decimal, what does it end up being?
.01.
0.01. Is 0.026 bigger or smaller than 0.01?
Say that.
Is 0.026 bigger or smaller than 0.01?
Bigger.
All right, so what's your decision? Do you reject or do not reject?
You don't reject.
Excuse me?
You don't reject, right?
Do not reject, that's right. You got to be careful when you convert your decimal, excuse me, percentage to a decimal, be sure to divide by 100. All right. Now, so notice it's a pretty small p-value, and yet if our alpha level of significance is 1%, we're not going to reject. What if I said the alpha is 5%? What's our decision now?
Then you reject.
Then you reject, yes, because 5% is 0.05 and 0.026 is less than 0.05. So you can see where this becomes kind of, a little bit, you might think kind of weird almost, right? Where it
I have a
depends on.
question.
Yeah, go ahead.
So where do we find the significant level at?
It'll be given to you in the problem.
Okay.
Yeah. Basically, picture short word problems where information will be given to you, where they'll tell you what that is. It'll either be called alpha, level of significance, or probability of a type 1 error. One of those three phrases will be used, and you'll know that's what the alpha is. All right, so you're absolutely correct. In the case of 5% level of significance, 0.026 is less than 0.05, and we would reject the null hypothesis. So notice that in many cases, when the p-value is neither too big nor too small, it's sometimes you can have different decisions based on what the level of significance is that you chose. So researchers have to be honest about this. They have to choose their alpha before they do any research. If they pick, for example, 1% as their level of significance, and they got this as their p-value, they can't just say, all right, nobody knows what I did, I'm just gonna fudge, and I'm gonna change it to a 5% level of significance, and therefore I can reject the null, which is what I wanna do. No, you can't really do that. That's not being honest about it. So it's basically, in many cases like this, you have to, it depends on the level of significance. That's why in step 6, let's go back to hold on a minute. Get back to the hypothesis test steps again. Step 6 talks about the interpretation. We always say the level of significance at the beginning of the interpretation, because What comes afterwards depends on what you said before here, when the level of significance. So in other words, in the case that we just saw, if I said at the 1% significance level, I would say there is not enough evidence to reject the null. If I said at the 5% significance level, I would say there is enough evidence to reject the null. See what I'm saying? So the interpretation has to have this little phrase about the significance level, because in many cases, that will determine whether you reject or do not reject the null. All right, that makes sense, sort of? All right, so what I want to show you, I want to actually created a couple screenshots of let me see what I have here. Here we go. I have all 4 of them up. So I created 4 screenshots. I guess I'll choose this one first. All right. So in this particular case here, first of all, looking at this, how many randomization samples did I choose in my simulation? How many did I choose?
$850.
That's correct. So in the top right-hand corner gives me the number of samples. So that's all these dots here, 850 dots. Now, you don't know which, now this is a dot, it says bootstrap dot plot of a mean, all right? Now, it doesn't say much else than this, that it's a bootstrap sample of one mean. If it was difference of means, it would say it here, okay? My question to you is, with what you're looking at here, is the alternative hypothesis going to be greater than, less than, or not equal to?
Say that again.
Is the alternative hypothesis, it's for a mean, so it's going to be mu, right? Mu is after the mu in the alternative hypothesis. Are we going to have a symbol like less than, greater than, or not equal to? Based on what you're seeing here.
Would it be not equal?
Right, because it's a two-tailed test. This box here, when it's checked, means two-tail, right? So not equal to, correct. Now, tell me the p-value. What is the p-value? Assume that I've already entered in one of these 2 boxes here, the sample mean. Remember, the sample mean you would enter in one of these 2 boxes. Suppose I entered the sample mean. I won't tell you which one it is. What is the p-value?
0.1.
0.1 is correct. That's right. Because it's the sum of these 2 numbers, right? It's a two-tailed test. So these 2 numbers here, when you add them, comes up to 0.1. 0.1 is your p-value. What if my alpha is 5%? Do I reject or do I not reject the null hypothesis?
It's do not reject, right?
Do not reject, right? Now, if you forgot, this is the reason I mentioned this. For a two-tailed test, if you forgot to add these 2 numbers together, right? And you said the p-value is 0.05, you would have said, all right, 0.05 is equal to 0.05, which is the level of significance. I would reject the null hypothesis. But the answer is do not reject, because you had to add these 2 numbers together to get 0.1, and that's bigger than 0.05, bigger than the level of significance, so you would not reject. That's correct. All right, good.
That makes
So, any questions about that? All right, So let me pick another one of these. This one. Same situation here. Same situation. All right. Now this is also a two-tailed test. Oh, is this the same? Is this the same thing? No, this is a different one. Different one. All right. Take a look at this one here. And tell me if alpha is equal to, so assume that one of these two numbers here, this one or this one, is the original sample mean, one of these two. I want you to determine at the 1% level of significance, do we reject or not reject the null hypothesis?
You say 1%. You say 1% of significance.
Yeah. Do we reject or not reject the null hypothesis?
We don't reject.
Okay, do not reject. Everybody agree with that? And why? What's the answer? What's the reason do not reject?
Well, the reason why I say we don't, because when you add it up, 0.070 as decimal, it'd be 0.14014, right?
No, it's point. Well, you're off by a factor of 10. It's 0.014. You use a calculator just to double check, because sometimes people make those errors. Go ahead, but you're still right, because 0.014 is bigger than 0.01. You're absolutely correct. But be careful with the adding these numbers, because it's 0.007 plus 0.007 is 0.014, not 0.14. All right, just be careful with that. All right, let's look at another one. I got a lot more here. Hold on a minute. This one here. Good one. All right. All right. Suppose the sample mean is 3. And what does the 3 represent? First of all, suppose, yes, tell me, there's two groups, group 1 and group 2. We don't know anything about these two groups. Okay. Tell me the alternative hypothesis. Please state it as U1 minus U2, and then give me the rest of it. So this is a difference in means hypothesis test. Please state the alternative hypothesis. U1 minus U2, and then tell me symbolically the rest of it. Yes, go ahead.
U1 minus U2 is greater than?
Greater than what?
Value, maybe.
Greater than what? No, I'm just asking for the alternative hypothesis. U1 minus 2 is greater than what number? Only one choice.
3?
No, that's the sample difference. Take a look in the middle of the dot plot. It tells you what it is.
0.
0. See, it says null is 0. That's the 0 difference. If you subtracted U2 from both sides of this null equation, you would get U1 minus U2 is equal to 0. Therefore, if it's a right tail test, it would be U1 minus U2 is greater than 0. Good. Does that make sense to the other person who mentioned the greater than? You know, remember the hypothesis tests are yes, good. are determined before you actually even do the sampling. So sample information is not relevant at this point. Okay, but the 3 indicates the following. X bar 1 minus X bar 2 is equal to 3 for that one sample that you have gotten. That's the one sample that you have, and you've entered 3 here, and tell me what the p-value is. Yes, go ahead. The p-value.
0.106.
Correct. And if the level of significance is 1%, do we reject or do we not reject the null hypothesis?
Say that one more time.
If the level of significance is 1%, do we reject or do we not reject the null hypothesis?
We do not reject.
Correct. What's the reason?
Because 0.16 is greater than 0.1. If I said
Yeah,
it right.
what? Yeah, 0.01. Yeah, 1% is 0.01.
Yeah, I keep getting that wrong.
Yeah. It's okay. Use your calculator just to double check when you divide by 100. All right, just because you don't want to make that type of mistake on tests, because I know you're doing it right. So just make sure that it's 0.01. Yes, you're absolutely right. We would not reject the null hypothesis. What if we did? And this is just a goofy example, but what if we made the level of significance 20%? Do we reject or not reject the null hypothesis?
Reject.
We don't reject. Oh, reject.
Reject, right? Because 20% is 0.2 and 0.106 is less than 0.2. We would reject in that case. But it's a bad example because nobody would ever pick a 20% level of significance. You know, probability of type 1 error, no one would ever predict one that high.
Can you get can you give another example of a significant level for it again, just like you did for 20?
Yeah. Oh, you mean with this?
Yeah.
So, yeah, all right. So what if we gave a 12% level of significance? Do we reject or not reject?
We reject, right?
Right. What if we had an 8% level of significance?
We don't reject.
Right. You got it. There you go. Very good. All right. We'll do one more before we leave. Let's try one more of these. Let's see. Which one did I not do? I don't know. Did we do this one? Not sure. I don't know if we did this one or not. No, we didn't do this one, right? Or did we? We did do this one. Sorry. Let me see if there, maybe I have them all. Do this one. See what this one is. I don't think I did. I don't think we did this one. All right. All right. Take a look at this one. This one is, if you read it at the top here, it's a difference in proportions. All right. We didn't do one of these yet. All right. In this particular case, please state the alternative hypothesis. P1 minus P2, and then give me the rest of it.
Is equal to 0.
So that would be the null hypothesis. What is the alternative hypothesis?
So the alternative is not equal to 0?
Correct. Then why?
I got no idea.
Can somebody help him out? We would say P1 minus P2 is not equal to 0. Can somebody tell me why? Well, it's going to, oh, go ahead. I'm sorry. Go ahead.
Oh, sorry, because we know it's a two-tail.
Yeah. I mean, in reality, before you do this, you would know by reading the problem that it's two-tailed, because somebody will say something like, I don't think there's any difference between the two proportions, you know? Well, no, I'm not, no, I'll say it another way. The researcher will
Okay.
say, most people think there's no difference in the two proportions. I do think there is a difference between the two. I just don't know which one is bigger than the other. Something like that, that would tell you that it's not equal to. So you do the two-tailed test. But the clue here, looking at the stat key graph here, is that we did do a two-tailed test, which means that the alternative hypothesis has to be not equal to zero, not equal to. In this case, not equal to zero, right? Because the null is going to be equal to zero. We subtract P2 from both sides of this equation here, you get P1 minus P2 is equal to zero. All right. And this is the last question. We have 30 seconds left. If I have a 5% level of significance, do I reject or not reject the null hypothesis, assuming that I've entered the sample mean, the sample difference of proportions in one of these two boxes here? I've already entered it. And I'm asking you is, do we reject or not reject the null hypothesis?
Are you a reject?
Reject. Okay. And what's the reason?
Because 5 is higher than 0. Correct, the p-value is 0.046.
All right. What is the P? So can somebody help this gentleman out? What is the p-value? He says it's 0.046. What is it?
So the p-value is 0.092.
That's correct.
Cool. Yeah.
Remember, it's a two-tailed test.
So
So
it's
we
always
have
in the middle.
only in two-tailed tests do we add up the two values in the two boxes here. So I was trying to trick you because by saying 5%, which is 0.05, if you forgot to add up these two numbers, you would have said reject because 0.046 is less than 0.05. But if you remember to add these two numbers, 0.092 is bigger than 0.05, so we don't reject. All right, so you have to be careful. You have to look at what type of test it is. If it's a two-tailed test, you add these two numbers for the p-value. If you have a left-tailed test or a right-tailed test, then whatever box you're looking at up here is the p-value. Okay?
Okay.
So I'll write up something and post it late Friday, early Saturday, which will show some of these examples, and then you can look at them also, all right? You'll have something that I'll post in Canvas for you. Any questions? Kept you just a couple minutes late. So no other questions. I'll